This is the 14th episode in a series about designing and building a clock for my relay computer. Last time I completed the schematic design, and so with that in hand, I can now move on to laying out and designing the final PCB. Before I get underway though, I want to cover off something I completely missed 2 episodes back when setting out the relay clock schematic. And that was only just the resistors and capacitors that form the delay circuit at each relay. So, quite literally the thing that makes the clock a clock. Nice job, Paul. Anyhow, to err is human as they say, and this is exactly why it's always worth printing these things out and literally going through each and every part of the design, ticking off the components and connections compared against the working prototype. Right, with that little bit of awkwardness out of the way, let's crack on with a PCB design. And to get things going, I've already set up a new PCB design file and set up the board outline, or rather, I've nicked the outline from one of my other PCB designs as I know for sure it's the right size and shape. The board outline though is simple enough and just consists of a series of lines and curves. You can see here, for the top line, the start X and Y and the end X and Y coordinates. Note here that the unit of measure is a mil, which is 1/1000th of an inch. This might look a bit odd for the metric lovers, but it makes sense here as the pad boards I originally used are on a 0.1 inch pitch, as are the breadboards I use, and as are a lot of through-hole components. 100mm is equal to 0.1 inch of course, and having my grid set to 100mm means it's easy to align components. Note that the board is made up of several design layers, and I can switch between them from here. I'll spend most of my time in the top and bottom layers, which is effectively describing where the copper should be retained on the top and bottom side of the board respectively. That is, this is where the PCB tracks will live. Below that, there's the silk layers, and these are where any legend, text or similar will go. The silk refers to the silk screen process, which is usually used for applying this layer to the board, but for small production runs like this, the manufacturer will likely use a form of inkjet printer to apply these layers. The remaining layers I don't need to worry about too much, as they'll automatically populate from my components. Near the bottom here though is the board outline layer, and that's where this currently selected line lives. This tells the manufacturer the extent of the board and where to cut it out from the larger PCB. And by larger PCB, I mean that usually the manufacturer will produce a single board with multiple designs from multiple customers, and then cut everything out and dispatch separately. It's batching techniques like this that help keep the costs for PCBs really low. I could, if I wanted to of course, move this line between layers, effectively making it a copper track or a printed line, but the outline layer is where this particular line belongs. Having this ability to move things between layers is handy though for moving PCB tracks from top to bottom, as we'll see later. Cool, what else then? Oh yeah, at the bottom here we've got 2 holes set out. These are defined with an XY centre point along with a hole diameter. Here the diameter is 137.796mm, which is 3.5mm. And that's common across all my cards, allowing for skewering 2 cards together, for the double height cards like the sequencer and controller, or for having something to grip onto when pulling the card out of its bay. So that's the basic card outline, let's get our components on there. And to do that, I go back to my schematic and update my PCB from there. Here I'm prompted to check my design as EasyEDA suspects there's incomplete lines. And it's right. But that's fine and expected and is coming from all those unused pins of the backplane connectors. I'll keep going, and after a short pause and a couple of dialogues, there we go. All the schematic components dumped just off the bottom right of the board. Now this placement is intentional of course and means if I added more to the schematic, then new components don't get randomly placed on the board itself, making them difficult to find. Zooming in, you might recognise many of these component footprints from my last couple of videos, and there's a direct one-to-one relationship with the schematic symbols and the footprints here. These footprints can be switched out for a different footprint if needed, but obviously there should be a match on the number of pins between the footprint and the schematic symbol. Right, let's get placing, and the best way to start is with the components that have a specific place on the board they need to be. A good example is these 4 IDC sockets which form the backplane connections of the card. I can select all 4 and then take them up the card to focus on that area. At the moment the sockets are facing the wrong way around, so let's rotate them 180 degrees. And I can then take the 20 pin socket into its correct location. And actually, how did I know that's the correct location? Well, it might be a bit difficult to see on this video, but the top leftmost pin aligns with a slightly thicker horizontal and vertical grid line. This is the grid origin, and I've specifically set this to tell me where to place the connections in relation to the card edge, and all my PCB cards have the origin set at that point. This 16-pin connector, marked P2, goes next, and again I'm using the grid to line things up. For this one, the leftmost pin needs 3 grid lines between it and the rightmost pin on the connector marked P1. Effectively, this means there's 400mm between the pins. Note also that the box above the pins also nicely butts up against its fellow connectors, but I'd never fully rely on that and always position things based on the pins and actual measurements taken from the physical component. P3 goes next, and then finally the 10-pin P4. Note that the box above P4 is slightly offset, and that's just down to differences in this footprint compared with the others. Again, in the real world, everything will line up nicely. Although the box will be printed on the actual PCB, it's not such a problem as the IDC socket will cover it up anyway. While I'm here, I'll also rotate the part IDs 180 degrees so they read the right way around when viewed from the card front. Notice again that these are all in the top silk layer, so will be printed on the card, whereas the pads for the pins are in the copper layer. Taking a closer look, you can see there's also a slight edge around each of these pads, and that's defining the gap in the solder mask that allows the pad to be soldered. Everywhere else, the solder mask is protecting the copper tracks and resists any attempt to apply solder to it. The centre of the pad is, of course, a hole to be drilled through the board. Speaking of holes and pads, that's all configurable too, and it's not uncommon to find that similar footprints have totally different pad and hole sizes. For me, I like to have a little bit more pad to solder onto, so I'll make these 70mm rather than 60mm, but I'll keep the hole at the 1.1mm, which is the 43.300mm shown. Looking at P1, you can see that the bottom left pin is square rather than round, and that's a pretty common design feature to identify pin 1 of a component. This is also totally configurable though, and here on P2 I can make its pin 1 rectangular, round, or even a custom shape if needed. In this case though, I prefer them all round, and making it easy to spot pin 1 isn't required, as it's not really possible to put the IDC socket in the wrong way around, or rather you quickly notice if the socket was the wrong way around. Over on P4 the pads are much larger, but that's intentional and fits nicely with the track design, as you'll see later. Quite handily, when you zoom in closer, you can also see what each of the pins are, and here we can see the V, ground and VD pins of the power connector. Scrolling left, P3 has the pins making up the DI bus, P2 is the address bus, and finally P1 is the control X bus. Cool, so that's the backplane connectors in place. The next thing that has a particular place to be is the user interface components. Let's start with the 6 LEDs I1 to I6. Worth noting here that these are very specific LEDs that have an integral resistor rated for 12 volts. Regular LEDs would just burn out here of course, and looking back at the schematic you can see there's a warning bottom left, but it's still a potential gotcha if you're not familiar with the schematic. Whilst we're here I can check on what each LED is for, and the first 4 show the relay ring counter stages, whilst the last 2 show the outgoing clock signal. As such, I'll physically group them together on the board like so. Again, I know exactly where to place them based on the grid and on what I've done on the other cards. It's important to be consistent here so that all LEDs are the same distance from the front of each card, creating a uniform look. Next, I'll place the switches, although worth noting here that one of these has a placeholder footprint as I couldn't import the proper one for the BCD rotary switch. S1 is the main power switch, and I'll place it at the right hand side, which means it will be at the top of the card when placing the computer. This means that when the toggle is up, it's on, and when it's down, it's off, which kind of just feels right to me, and as with the LEDs, it's important, at least to me, to keep everything consistent and make sure other switches follow the same pattern, user interface, and experience. Again, I've measured the switch to know how far from the front of the board I need to place it. Where it is now just leaves a little bit of the toggle jutting out from the edge of the board, making it easier to operate. I'll place the rotary switch next, and again, based on a physical measurement, I know where I need to put it. Where it is now makes it look like it's much further forward than it should be, but it's a much smaller component compared to the switches. Last up on the UI is S2, which lets the user choose between the relay or crystal-based clock. If the switch is up, or to the right here, it's the crystal, and if it's down, or to the left here, it's the relay clock. To my mind, it kind of just makes sense that when the crystal is selected, the toggle of the switch is nearer to the neighbouring rotary switch, given that adjusts the frequency of the crystal clock. I'll just tweak those switches around a bit now so there's some symmetry between the switches. Again, this is all just aesthetics and so on, but there's something in me that really likes things being lined up and neatly ordered, which is probably me giving up a little too much information, but there we go. Although that said, the rotary switch is actually too far forward, so let's fix that. As with the IDC connectors earlier, I also want to make the pad and hole sizes consistent. And here I'll go with the LED's pads of 60mm and 0.8mm hole and apply them to the rotary switch, which also has very small pins similar to an LED. I'm happy with the pads and holes for S1 and S2, and actually that needs pretty big pads as the solder isn't just for making the electrical connections, but they also anchor the switch down and support the mechanical pressure when the switch is operated. At this point you might be wondering what all the blue lines are going everywhere. These are called rat lines and indicate where a connection to another component is needed. The game effectively is to keep laying down tracks until all the rat lines have gone. One thing I can do to make a big leap forward on that is lay down a big copper area that can connect common things together. This is really common in PCB design and is often used for power or ground planes, especially in boards that have internal layers. Here I'm on a 2-layer board, which keeps costs down, but does mean my ground planes need to share their space with the various tracks I'll be laying down, as you'll see later. Here I've brought over a copper area from one of my other boards to save time, but as you can see it's really just a list of coordinates describing the various points of the shape. Here I also like to have rounded off corners, so I define 2 points at each corner and then set the radius of the arc I'd like between those points. As with everything else on the board, these values are in mil. I also need to set the direction of the curve using the drop down here. Each copper area needs a net to connect to, and this one is set to GND for ground, and that means it now shares the same connection as any other component also connected to ground. As with components, this can sit in the top or bottom layer, and actually here I'm going to duplicate the area and put it into the bottom layer so that I have a kind of copper sandwich. Not that it particularly matters for this circuit, but having these ground layers can guard against electrical noise in a circuit, so it's considered good practice. It also helps with thermals and so on, but here really I'm just after simplifying my ground connections. Now at the moment it doesn't look like anything has happened, but the copper area has been calculated, it's just that it's currently hidden. That's intentional, and as you'll see, hiding these is a handy feature when designing a board. I can unhide it though, like so. And here you can see the bottom layer area in blue. And switching to the top layer, you can see its copper area in red. If I zoom in on the power connector now, you can see how the 4 ground pins are joined into the copper layer. Note how it looks like a little cross? And that's there to create some thermal relief. If it was a solid connection, then when you try and solder the pad, the large copper area will just wick away the heat from the soldering iron. With a pad connected like this, it limits that effect and makes soldering easier. Notice also that for the other pads, there's a clearing between the copper area and pad, and this ensures they can't be accidentally joined when soldering. Again, this can all be adjusted and changed, but the default clearing values work just fine here. Switching to the bottom layer, you can see that it's the same, and it's also worth noting that the hole at each pad is internally plated, meaning the pad on the bottom layer is always connected to the pad on the top layer, and therefore it follows that the top copper area is now connected to the bottom copper area through these 4 pads. If we go for a wander down the board, you can start to see the real value of this ground plane, as the ground shield around switch S1 has automatically been connected to the ground plane. Same for switch S2. But even more usefully, the cathode of each LED has also taken its ground connection from the copper area I've created. So already that's taken care of quite a lot of the rat lines that need routing. Finally, if we look at the drilled hole at the edge of the card, you can see there's also a clearance around this, ensuring I don't electrically connect the screws to the ground plane. Bearing in mind there's also the solder mask layer on top of the copper, which does add some extra protection, but ideally I'd pull the copper area back even further to allow for the diameter of the screw head. As I go through designing this board, it's always good to pop into the 2D preview now and again, which will show what the card would look like when manufactured. You can see here where copper will be retained as a lighter blue and areas without copper as a darker blue. This reflects what you'd see in real life, as the copper areas reflect more light, so appear lighter under the solder mask. I can flip the board over, which also flips the image left to right, just as it would if you were holding the physical card. And I can even change the colour of the solder mask. Here, I'll set it to the more traditional green colour, but you can order PCBs in any of the listed colours. Likewise, you can also change the surface finish from gold to silver, and in my case I'll be going for the cheaper Hassel finish, HASL, which will result in the silver colour. Right, I think you get the idea now, so let's jump forward in time to here, and you can now see I've positioned all the required components onto the board. But note, all of the rat lines remain, and routing those lines in copper will be the next major task to complete. Where components are placed and how tracks are routed is one of the things I love about PCB design, as you can get a dozen different engineers to design this board, and on the whole they'll come out with a dozen different designs. There are some basic rules of course, but there's also an element of, dare I say, artistry and aesthetics, and my placement of the components here is very much down to what makes sense to me and what I feel looks right. Naturally enough, things that belong together are placed together, and this logical placement ensures connections will be kept shorter on the whole. A certain amount of space is kept between components, and that allows for any heat to dissipate in air. There's also a kind of front to back order going on here, where, like in the crystal clock for example, the signal is built up in stages as you progress up the card, from the crystal at the front, through the frequency dividers, and then onto the selection and relay driving. As I go through routing tracks, I can always move these components around of course, but really you would want to get a pretty good layout by this point, as it gets harder and more fiddly to move things around as the more tracks are routed. Something worth making friends with early on is a DRC, the Design Rule Checker, which will warn if there's any design problems, things like pads too close together or tracks crossing over, etc. It can also tell you which rat lines are still to be resolved and need committing to copper. As you can see, I'm currently scoring 75 out of 129, so it goes to show just how much time that ground plane has saved, as I'm nearly 60% of the way already. Speaking of the ground plane saving time, I can pull a similar trick for the power supply lines, as this is a commonly used connection on most of my boards. Here, if I zoom in on the bottom layer, you can see how the rat lines spread out from the V line of the power connector. Here, relay K6 wants two connections to it, and also down here at switch S1. Well, let's create a copper area to join these together, and firstly I need to select which net this plane will connect to. In this case it's the incoming 12 volt supply V. I can now start plotting out the area, clicking the mouse at every place I want to set a point in the shape setting. Around switch S1 I'll make a bit of a boot shape to get at that middle pin, remembering that I need to ensure there's enough space around the other pads so the copper isn't too thin coming into S1. I can then go back up the board to close in around connector P4. Notice I'm making a diagonal line at the corners. This is where I'll set a radius later to give a nice rounded corner. From here I'll go over to the top of the card and come down between P1 and P2 to land around relay K6. From there it's back up the right hand side, over the top of P2 and back over P4 to complete the shape. With a final click the area is complete and fills out in blue, showing where the copper will remain on the bottom layer. There we go, that's those V connections hooked together via a copper area. Now, how far can you go with that concept? Well, I'll show you. So this is maybe an hour or so later, and I've laid out the 12 volt power line, the power from switch S1 to S2, the relay clock power, the crystal clock power, and then the crystal clock power disconnect. Around all of that is the ground plane. And don't be fooled into thinking there's some automated magic going on here. To get total control of how it looks, this is a defined copper area that basically runs parallel with all the other copper areas on this side of the board. And this is arguably a step too far, but I'm treating myself as I quite enjoy laying down these areas and making the gaps and curves all nice and neat. Now there's nothing stopping me just stamping down a single track to do all these connections, but there's something deeply satisfying, to me at least, in designing something that looks, in my opinion, this pleasing to look at. One last thing I do need to do power-wise though is connect these two VD pins together, and for that a regular track is absolutely the right thing. I'll just bring the track size down to something more suitable for the pads, and then there we go, track laid. Now notice how it looks to merge with the copper area around it, and this is because I need to recalculate that copper area to deal with that new track. This is crucial, as if I put this into production, I'd now have a short between VD and ground on this board. A click of the mouse though is all it takes to rebuild the copper area, and you can now see the copper area is pulled back around the VD pads and track. Right, it's time to convert more rat lines to copper tracks, so it's off to the top layer, and I'll hide the top ground plane so I can see what I'm doing, as otherwise each track I lay will look to disappear into the ground plane until I rebuild it. I'll start on the relay clock and go for some of the internally connected components first. Let's start here with the RC components and the diodes. Here I'll use a 20mm track, as that'll fit nicely around the components and can take up to 2.5 amps, which is obviously way more than will be running between these components, but better to over-engineer rather than under, I guess. As I start each track, it'll automatically set the net of the track to whatever the net of the pad is. It also, rather helpfully, shows in white what nearby components want that connection, and even better, resists you accidentally connecting to something using a different net. After that, it's a bit of repeat, repeat, and repeat, and so on, and so on. What's quite nice is it'll automatically put in 45-degree bends for you, which keeps everything nicely lined up and consistent with the grid spacing. Right, that's the relay power and RC network done. Zooming out now, I can rebuild the copper area, and you can now see how it's pulled back around those tracks I've just laid down. Marvellous. Right, let's skip forward in time again, and you can see I've now laid down all the internal connections in the relay ring counter. These are done with 10mm tracks, which means I can squeeze nicely between pads, leaving enough clearance but still carry around 1.5 amps. This is way more than I need, as each line will ultimately only drive a couple of relays either somewhere on this card or elsewhere in the computer, and given each relay draws around 10mA, it's not really a concern. What's quite nice in this software is even though I've laid tracks, I can grab individual segments, like this, and move them around to even up the gaps and make things fit better. Now I could obviously get carried away with this, but this will do for now. Or maybe just a bit more. Nah, that's enough for now. Note though that if I get too close to a pad, the DRC will mark up the issue with an X. Heading down the board, you can see I've also tracked up the 4 LEDs, and to avoid having to cross lines over, I've passed the tracks down and then around to effectively change the order of the tracks so that I4 is now on the left and I1 on the right. As before, I can drag segments of those lines to move them around, and although by default they snap to the grid, I can also override that to get a more precise placing. I tend to keep this for the diagonals to get them spaced equally just as they are for the vertical and horizontal segments. Again, the PCB itself isn't bothered about where these tracks are placed as such, it's more just for the aesthetics. So let's rebuild the copper area, and that's now pulled back a bit to fit in the tracks I've been moving around. Looking at the 2D preview again, you can see the fruits of my labour so far. Cool. Carrying on, you can see there's these rat lines still to go on the relay-based clock circuit. However, you might have spotted that these tracks going down to the LEDs are blocking my way. Well, the way around this is to use vias. So here I'll take a track up, and at this point I can add a via. This is a tiny plated hole that goes through to the other side of the board, and I can now continue the track on the bottom of the board, shown here as a blue track segment. I can then drop a via here, to bring me back to the front of the board, and from there I can route as usual. Let's do the same for this next track. Up, through, up, and back again. The next one is interesting, as a rat line is shown at the shortest distance between pads, but actually I can pick this one up over here and take a track up through the relay pads, through the board, under the LED tracks, and back through another via. For this one I can pop a via into the existing track like so, and then track under, and via back. With those done, I can now lay down tracks on the top side of the board as normal to connect everything together. There we go. Whilst I'm here, I'll also squeeze the freeze line out between these pads. Right, another jump forward, and you can see I've now laid down all the needed tracks, and looking at the DRC, we can see that's 129 of 129 nets. There's also no DRC errors, which is just lovely. Taking a look at the 2D preview, you can see all the tracks, but there is something I'm not totally happy with. Take a look over here at U3 and you can see some ugly gaps in the ground plane, and this is because there's not enough room for the copper to flood through from around the component. It's literally cut off by the tracks going between the IC's pins. Likewise over here on relay K5, it's even worse with big areas cut off by the tracks. On the bottom side of the board, you can see where the vias come through and back again, but these aren't impacting the planes on this side so much. It's always worth checking though. The DRC will pick up any outright issues, but it's important to make sure there's enough width of copper in the planes to supply power or take ground where it's needed. Anyhow, those ugly gaps are easily sorted, and all it takes is a via, and if I set this one to ground, and then rebuild the copper area, it then fills this area as it now has a way of reaching the ground plane. I can repeat this via trick for the other gaps, but sometimes it's just better to reposition the surrounding tracks and so on to allow the copper plane to flood through. Similarly here for the RCA track, I can simplify things a little by taking the via here rather than here, and then join the two vias together like so. That now tidies up the ground plane, like so. Okay, jumping forward again, and I've tidied all of the copper planes up, and it's now time to start labelling things up a bit. Firstly, I'll add the card name down the right hand side of the card, and I've nicked this from the Y register card so it's consistent, and then I just change the text like so. Popping into the 2D preview gives an idea of how it'll look in real life. Next, I'll get some labels placed along the front of the card for the UI. These are a bit of a redundancy, as each card has a plastic strip that carries a legend, but these are quite useful when testing the card independently of the computer. Again, here is what that's going to look like in real life. Okay, so you get the general idea, so let's skip forward, and I've gone on a bit of a labelling spree. I've labelled out the broad functional groups of components, but also made clear the divide between the relay-based half versus the crystal-based half. On the bottom layer, I've also been labelling, but in a slightly different way. Here the labels are on the copper layer, so will be etched in, and as such the surrounding copper area pulls back to make space for the text. Again, this is a stylistic choice rather than anything particularly functional. Here's a 2D preview of the top side, and I personally think it's quite pretty. Again, remembering that any PCB design is always going to be quite individual to the designer, and I love that about PCB design. Right, so that's the PCB design done, so let's move to getting it manufactured. Now, unsurprisingly, EasyEDA has close ties to JLC PCB, given it's all the same company, but there's nothing stopping you generating the Gerber files and taking your business elsewhere. Let's take a quick look at that now, and I'll open them in Cuprum just to prove the PCB design is completely independent of EasyEDA. Any manufacturer should now be able to take these Gerber files and make your PCB. But I'm happy enough with this service I've had from JLC PCB over the years, and so that's where I'm heading now. Clicking one-click order uploads the Gerbers and starts the order process. From here I can now play with the options, but first I'll switch it to UK pounds so I can work out how much I'll be spending. And straight off the bat, With all the options set to default, this is only going to cost £9.50 for 5 boards. Now that's just stupidly cheap in my opinion, and this isn't a sponsored video by the way. Let's take a wander through the options. Firstly, the base material is the pretty standard FR4, but if you wanted to get swanky, you could have aluminium. I've designed a 2-layer board, so that's what's selected, but you can go for 4 or 6 layers, but that does increase the price quite a bit because it increases the complexity to manufacture the boards. This is also why I put the ground and power planes on the outer layers, but if it was a really complex board, it's better just to cough up the money rather than try and design around it. Likewise, the dimensions are already defined by the uploaded design, and here it's 115mm by 160mm, which is the standard size for my computer cards. Quantity wise, the minimum you can order is 5, but you can, of course, order more in the batch. I'm just going with the consumer electronics as a product type, which is exactly what this is, but you can pay extra for aerospace or medical requirements to be enforced. Something you can do is panelise your design so that it's actually several PCBs in one design, but you do need to tell JLC PCB what you're up to so they can price and process accordingly. Now a more obvious choice is thickness and colour. Here I'll go for the standard 1.6mm thickness, but more or less is available. Likewise, green is the traditional colour, if you like, of PCBs. There's actually a good range of colours, but it does increase the delivery time because, of course, JLC PCB needs to group these orders together to manufacture them as a single larger PCB and then cut them down. Price-wise it doesn't make a difference, it's just in the turnaround times. Copper weight I'll also leave as is at 1 ounce, but you can double up to 2 ounce. And now this does of course have a big impact in the terms of track widths you use, as more copper equals more current carrying capability. So this is a decision you really should have made before you start designing. The next one is interesting and is all about how the pads and exposed copper will be finished. That is, what surface treatment will be applied. With Hassel, the board is dipped in molten tin and then the 2 air blades blow off the excess. This results in a thin flat layer over the copper. Now I'm going for lead here rather than lead free as it solders a lot better in my opinion, but does mean I shouldn't be breathing in the fumes when soldering or try to lick the board. There's also ENIG, which gives a nice gold finish that looks particularly good on the red boards, however it's also not cheap either. Ouchie. Yeah, I'll stick with the Hassel thanks. For each of these options there's a link to the JLC PCB website that explains more about the option, and it certainly explains things better than I can here in this video. And in that vein, I'll skip these last couple of options as they're quite specific to the use case. The last one is interesting though, which is where the JLC PCB will place the order number. This is needed, otherwise they'd have a nightmare picking all of the boards out from all the others come dispatch time. You can choose, and pay, to have this removed, but a better option, in my opinion, is placing the text JLC, 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 JLC on the board for where the order number can be placed. Typically that will be under where a component will be soldered, and on this board I'll pop it under one of the backplane IDC connectors. Right, that'll do, and you can see the price is still £9.50, so that'll do me nicely. One thing to remember though, of course, is this needs shipping, and that's understandably not included in the price. You do get plenty of choice for this though, and if you want it quickly, you pay more, and if you can wait, you pay less. It of course makes sense to do several orders at the same time so that you can save on delivery, and that's exactly what I'll be doing here behind the scenes for other bits and bobs in my computer. So, there endeth my board design, and likewise this video. This series is also nearing its end because when the boards arrive from China, all I've got to do is solder it up, give it a test and then fit it to the computer, and finally the clock for my computer will be complete. As always, thanks for watching if you've made it this far, and I'll see you all next time.